Okay, so we're officially recording.
Yes, we started recording.
Okay, so today we have the pleasure of having Russel Avdek of Uppsala University, who's talking about holomorphic curve invariants of the exchange type, an algebraic Giraud criterion.
Yeah, so in the last, I guess since I posted my abstract and title, Yorgos here at Uppsala has been able to help me out with some homological algebra, which I'm not very good at. And so I have a few new results, and now the title of the talk is an algebraic Giraud criterion. And before I start, I just want to say thanks to the organizers, obviously, for the invitation and for all your hard work during these strange times. And also thanks to all the speakers for your great talks. And I hope everyone at home is staying healthy and safe. So what's our goal for today? Or rather, what's our dream that we want to accomplish? And that's, we want to know what a neighborhood of a convex hypersurface is tight in any dimension. And so that means we want to find a generalization of Giraud's criterion to all dimensions. And so that sounds like a really difficult problem, and I have no idea how to solve it. But instead, we can try to think about the problem algebraically. And today we'll detect algebraic tightness using variants of symplectic homology.
In dimension 3, or?
Sorry?
In dimension 3?
Well, we're going to do all dimensions today.
Okay, very good.
Yeah. So, and so because we're at the Giraud-Viterbo birthday celebration, I'll be talking about analyzing Giraud submanifolds using Viterbo's invariants, convex hypersurfaces, symplectic homology. And so a brief outline of the talk is we'll describe what is a convex hypersurface, what are the holomorphic curve invariants I'm going to use, we'll state the main results, and then we'll work through some examples, the classical three-dimensional case, and some relations involving mapping class group relations, and then we'll sketch the proof of the main theorem. So to start, we'll take a 2n plus 1 dimensional contact manifold MC, and I'm going to abuse the definition of a convex hypersurface a little bit to suit my purposes. But for us, a convex hypersurface will be a hypersurface in M such that it has a neighborhood of the form interval times the hypersurface, and we'll always parameterize the interval with the variable tau, such that the contact structure is tau invariant. And so if we choose a contact form, which is also tau invariant, we can write it alpha is equal to f d tau plus beta, where f is a function on the hypersurface and beta is a one form on the hypersurface. And that gives us a decomposition of S into a negative region, a dividing set, and a positive region, which I'll call S minus, gamma, and S plus. And on the positive and negative regions, those are defined where F is non-zero. And on those regions, plus or minus F inverse of beta gives us a complete Liouville structure. And on gamma, we get a contact structure. And so I'll color code things blue for the negative region, purple for the dividing set, because we know that contact geometry is purple, and red for the positive region. And so for the purposes of this talk, we want our intuition to be that the S plus and S minus are going to give us two Liouville fillings of the dividing set. And so convex hypersurfaces have been extraordinarily successful in studying contact manifolds in dimension 3. And here's some of the strategies which have worked out really well. So first, we can try to characterize whether the ambient contact manifold is tight or over twisted in terms of the existence of convex hypersurfaces with certain properties. Two, we can do like a Haken type decomposition, cut our ambient contact manifold along a convex hypersurface and then study the smaller pieces. Or a third option would be we can encode some global topology of the contact manifold as some Legendrian submanifolds would sit in the hypersurface. And so one of the, in dimension 3, we have a lot of tools at our disposal. The most fundamental one is Giraud's criterion. And it says that if a hypersurface in dimension 2 plus 1 is a sphere, then the neighborhood of it is tight if and only if the dividing set is connected. And if the Euler characteristic, or if it's anything other than a sphere, then it's tight if and only if the positive and negative regions have no disk components. And so, this is excellent. We can go really far just with this easy to use tool. So what are we going to do when dimension is higher? So we can try some H-principle type techniques, and there's some recent papers of Honda and Huang which apply this strategy. We can look for plastic Struve-like objects, and that group also employs that strategy, and there's some recent paper by Chang and Niederkruger, which also do this. And our strategy will be to employ floor and SFT type techniques. So what are the invariants we're going to use? The invariant is sutured contact homology. And so this is an extension by Colangagini, Honda, and Hutchings of the Eliashberg-Giventhal-Hofer contact homology to contact manifolds with convex boundary. So we take, from 30,000 foot point of view, we take a contact manifold with convex boundary, and to it contact homology assigns a unital DGA. And when we have a codimension 0 inclusion of one contact manifold into another, this gives us a unital DGA morphism. And so that means that any algebra, any unital algebra can map to the 0 algebra, but the 0 algebra can only map to the 0 algebra. So it has this kind of nice functorial property. And we'll say that a contact manifold is algebraically overtwisted. This is a notion from Niederkruger and Bourgeois. If the contact homology is 0, is there some objection? And this is because if the contact manifold is geometrically overtwisted, then the contact homology will indeed be 0. And if the contact manifold embeds into anything which is closed and label fillable, this tells us the contact homology is non-zero. And so if you like embedded contact homology or Hegardt floor, we can think of the unit in the contact homology algebra as being our contact class. And so that means that if it's not equal to 0, then we know that our contact manifold is tight. And as most people are already familiar with, these algebras are generated by closed Reeb orbits with a grading which is the Conley-Zender index plus n minus 2, because my contact manifold is 2n plus 1 dimensional. And the differential counts J holomorphic curves and the symplectization of the contact manifold with one positive puncture and any number of negative punctures. And so another flavor of contact homology is linearized contact homology. And here, instead of MC, I'll suggestively use gamma C gamma for my contact manifold, which is 2n minus 1 dimensional. And when we have such a contact manifold with a Liouville filling W, then we take the vector space of Reeb orbits in gamma. We grade them according to Conley-Zender indices again, and we count holomorphic curves with 2 levels. The top level is a holomorphic curve and its symplectization with at least one negative end. And then we cap all but one negative end with a holomorphic plane in the filling W. And this defines our linearized contact homology differential. And the result gives us this additive group called linearized contact homology. If you prefer floor theory, this is the same thing as S1 equivariant positive symplectic homology with grading, or the twist on the grading. And so this is the version I'm talking about is due to Bourgeois-Oncha. And I think the original definition is due to Viterbo and also fits into the SFT framework. And so when we have this invariant, we have this augmentation homomorphism, which just counts holomorphic planes. And on the chain level, there's a chain map, so it descends to homology. And I'm going to call this count of planes epsilon sub W. And so today we'll be talking about a new invariant called bilinearized contact homology. And so we have now 2 different fillings, or possibly different fillings, of our contact manifold gamma. And so we have 2 ways to count planes. The fillings are called S minus and S plus. The counts of planes I'll call epsilon minus and epsilon plus. And we define the bilinearized contact homology differential by counting, by taking holomorphic curves in the symplectization of our contact manifold with at least one negative puncture, and then capping off all but one negative puncture with planes in either of the symplectic fillings. And the bilinearized contact homology differential also has an augmentation, which comes with some signs called, and I'll write it epsilon plus minus epsilon minus. That's exactly what you think it is. The count of planes in the positive filling S plus minus the count of planes in the other filling, S minus. And this gives us a chain map and a homomorphism from the bilinearized contact homology to the rational numbers. And so this is, the reason I call it bilinearized contact homology is because this already exists in the Legendrian case. It's an invariant defined by Bourgeois-Chantrain. And their definition is defined by counting holomorphic disks. And when you have a holomorphic disk, you have boundary punctures and you can order the boundary punctures. And so you have a good notion of left and right. We're working with interior punctures on a simply connected Riemann surface. And so there's no notion of ordering of the punctures. And so now that we have this, we're ready for our main results. So I'll write V for my vector space of orbits in gamma, which is my dividing set. And I can shift the grading up and down if I want using this thing I'll call sh. And the main theorem is that there exists contact forms, almost complex structures, virtual perturbations, and orientations such that the contact homology of our neighborhood of our convex hypersurface can be computed as follows. Its algebra will be generated by the orbits in gamma, shifted up in grading by 1. And the differential applied to an orbit is the count of planes in S plus minus the count of planes in S minus. So that gives us our 0th order term, plus the bilinearized contact homology differential. And so those count holomorphic cylinders. And so d squared is equal to 0 in contact homology tells us that bilinearized contact homology is a homology theory, and that epsilon plus minus epsilon minus is a chain map. And so,
Russel,
yes?
what is SH and SH minus 1?
Oh, those are the grading shifts.
Oh, okay.
Yeah, so those are, you can more or less ignore them. Any other, or maybe I'll state some things and then I'll take some questions. So in defining this kind of thing, what I wanted to do was compute this contact homology, and then this bilinearized contact homology just kind of fell out of it when I was trying to solve some transversality issues. And I'll note that something similar happens. There's an open string example where Ekholm studies also some kind of like symmetrically defined Legendrian submanifolds, and he ends up getting something almost the same in the Legendrian contact homology case. And so being that we have this computation, the differential is very nice. We can exactly tell when our contact homology of our convex hypersurface is 0 or non-zero, and that's our algebraic Giroux criterion. And the statement is that the contact homology of our neighborhood of our convex hypersurface is non-zero if and only if the count of the epsilon plus minus epsilon minus is 0 in the bilinearized contact homology. So roughly speaking, there's some formulas, what's actually going on. Roughly what's happening is that the neighborhood of the convex hypersurface is algebraically over-twisted if and only if the counts of holomorphic planes in the positive and negative regions are sufficiently different. Any questions before I move on?
What is it saying in dimension 3? In dimension 3, do you know that the tight neighborhoods of convex surfaces are algebraically tight too? Can you recover the three-dimensional criterion?
Yeah, so that's exactly my next slide is that when we're in dimension 3, we get exactly Giroux's criterion, which is that the contact homology of our neighborhood of our convex hypersurface is non-zero if and only if the neighborhood is tight. And so how do we see this? Well, so according to the contact forms we're going to use, which we'll see later in the talk, each connected component of the dividing set gives us a single embedded Reeb orbit. And the bilinearized contact homology just vanishes identically. And so all that's left are the counts of holomorphic planes in the positive and negative regions. The counts of holomorphic planes in the positive and negative regions are exactly is 1 if the component is a disk, and 0 otherwise. So I'll work through a couple of examples here. The first is if I just take the 2-sphere with the dividing set just being the equator, then so each disk component contributes a holomorphic plane. And we count the positive region with a plus sign and the negative region with a minus sign, and those cancel out to be 0. And here's another 2-sphere, which has 2 connected components of its dividing set. So if I take one of them, it bounds a disk on one side, and that means that its augmentation will be a +1 for that side, and then a 0 for the other side. And so that tells us the epsilon plus minus epsilon minus of that reorbit is 1. And that tells us, based on our formula for the differential for contact homology, that the unit in contact homology is exact. And so the whole algebra vanishes. Any questions so far? So now we'll do some of my favorite examples, talking about stuff I'm totally unqualified to talk about, algebraic geometry. So here's some really cool surfaces embedded in some holomorphically embedded in some 4 manifolds. So I'm going to take a divisor, which I'll call z minus d in CP2. This is going to be a divisor of degree 2d. And then I'm going to take a divisor I'll call z plus d in P1 times P1 of by degree D2D. And so if I look at these 2 divisors, their surfaces, which they're closed Riemann surfaces, their self-intersection numbers are the same, and their Euler characteristics are the same. And so Weinstein's neighborhood theorem tells us that the tubular neighborhoods of these divisors are, from the point of view of symplectic geometry, the same things. And so what I can do is I can take some holomorphic pencils associated to some line bundles over P2 and P1 times P1. And this will tell me that the complements of these divisors are Weinstein manifolds with some preferred Lefschetz vibrations. So I'll call CP2 minus Z minus D. I'll call that S minus D. And P1 times P1 minus this divisor, I'll call this S plus D. And the Euler characteristics of these are clearly different, but they have the same Booth-B-Wang bundle structures on their boundary. And so those are circle bundles over these Riemann surfaces with Chern number minus 4d squared. And so what we can do is we can take these 4 manifolds and we can build an asymmetric convex hypersurface out of these 2 pieces, being that they have the same boundary. And so I'll call that SD. And again, the negative region is the complement of a divisor in P2. The dividing set is this Booth-B-Wang circle bundle over a Riemann surface. And the positive region is the complement of a divisor in P1 times P1. And so, you know, these kind of 4 manifolds come up when you're studying Lefschetz vibrations and mapping class group relations from a holomorphic perspective. And we'd like to know, are these neighborhoods of hypersurfaces I've constructed tight or over twisted, or at least algebraically, are they tight? And so the theorem is that when D is bigger than 1, the contact homology of our neighborhood of our hypersurface is not 0, so that these neighborhoods are tight. And for D is equal to 1, the contact homology does vanish. And I have no idea if these things are tight or not, or if this thing is tight or not, because it's just for this D is equal to 1 case. And so here's a sketch of the proof of the theorem. So we're working with, so the first part is, as I think almost every single talk at this conference so far, I have to talk about some of Bourgeois' Morse-Bott techniques. And so we apply the Morse-Bott technique to this Booth-B-Wang bundle. And what it tells us is that the bilinearized contact homology is equal to the cylindrical contact homology of this manifold gamma, which is just this circle bundle over a Riemann surface. And so now that's kind of easy. The next thing we want to do is we want to relate counts of holomorphic planes, which are asymptotic to the Reed orbits on this thing. In these divisor complements, we want to relate these counts of holomorphic planes to just counts of holomorphic curves in P2 or P1 times P1. And luckily, there's a lot of easy arithmetic which helps us out here, classical arithmetic, which is quite beautiful. So in a d greater than 1 case, we sort of mix that arithmetic with these Morse-Bott index theory, and it tells us that there's no holomorphic planes to count. And so this augmentation has to be 0, and therefore our contact homology has to be non-zero. So we know that these the convex hypersurface we've built from these two hypersurface complements or these two divisor complements is tight. In the case d is equal to 1, we can relate these, again, we're relating these counts of holomorphic planes to counts of holomorphic spheres. And if you want to count holomorphic spheres of the type line times point, passing through point times point in P2, or P1 times P1, then that's exactly 1. And that tells us, when we combine it with the index theory, that the epsilon plus augmentation is non-zero for some orbit. And it's on the negative side, the epsilon minus gives us 0. So that tells us, that count of planes tells us that the contact homology of this thing is 0. And so this d is equal to 1 case is a very special, they're a very special pair of manifolds. The divisor complement in P2 is a Lefschetz vibration whose fiber is a 4-punctured sphere, and it has 3 vanishing cycles. And those correspond to 1/2 of the lantern relation. And on the P1 times P1, we have a Lefschetz vibration whose fiber is a 4-punctured sphere. And this has 4 vanishing cycles. And this gives us the other half of the lantern relation. So I think I learned about this reading some expository articles by Aru and Smith and Seidel from a few years back. And the other interesting thing to note is that the Boothby-Wang bundle in the d is equal to 1 case is in lens space L41. And according to McDuff, this is the only LP1, which is a quotient of the standard 3-sphere with more than 1 symplectic filling. And so an open question to the audience is, what positive mapping class group relations determine tight or over-twisted neighborhoods of convex surfaces? So I guess if you have any mapping class group relation where all the den twist involves are positive, you can construct one of these convex hypersurfaces and ask, is it tight or not tight? So I don't know. It sounds like an interesting question. I don't know very much about it right now. Any questions so far?
Yes, I have one question. Does your do your convex hypersurfaces sit naturally in some 5-dimensional contact manifold?
That's a great. So I think that's a great question. So my current perspective is that Honda and Huang established that there's some C0 genericity of convex hypersurfaces in high dimensions, like in dimension 3, there's C infinity genericity. So these things should be everywhere. What do they look like? I have no idea. So yeah, I sort of can't think of any. The only way I can think of this sitting in a 5 manifold would be just to, instead of taking the hypersurface times R, take hypersurface times S1. But perhaps there's some sort of more natural place they live or can be found.
I think, Russel, can you prove that the hypersurface times S1 is also algebraically tight? And, I guess so.
Oh yes, because you would, in that case, you would just lift to the universal. You just take the hypersurface times S1, just lift to the universal cover, and then you have tightness on the universal cover that tells you that the S1 times the hypersurface is also tight.
But if it was about geometrically over-twisted, yes, because the over-twisted disk would lead to a.
Oh,
but
yeah.
in the algebraic over-twisted situation, does it work? Yeah, I guess so, because everything is periodic, so presumably the holomorphic curves cannot escape to infinity.
Yeah, to do it geometrically, there's sort of there's more to worry about that I'm not sure how it works, but it sounds completely plausible. Because there's the holomorphic curves in the dividing set that'll give you some kind of Morse-Bott thing you can easily analyze, and then there's the kind of some reorbits which stick straight up and straight down along the positive and negative regions. So how that all fits together, I'm not exactly sure. But.
Another variation would be to consider non-trivial circle bundle, because in the three-dimensional case, the zero criterion also applies for S1 invariant contact structure on non-trivial S1 bundle, not only on neighborhood. There is also a version of the criterion.
Yeah, if you kind of have a surface, if you have an S1 bundle, and maybe you have some monodromy, then you know those things are geometrically tight because you can again just kind of lift to a cover. But in terms of the holomorphic curve theory, I'm not quite sure. But I would anticipate that they're probably, I would conjecture that they're all algebraically tight. Okay. Any more questions, or shall I move on to the technical stuff? So now we'll give an outline of the proof of the main theorem. And just to restate what it is, we have a graded vector space of Reeb orbits inside of the dividing set gamma. And the theorem says there exists a contact form alpha, almost complex structure perturbations and orientations such that the contact homology can be computed by taking the Reeb orbits in the dividing set, grading shift up 1, and using the differential is the count of planes in the positive region minus the count of planes in the negative region, plus the cylindrical term, which is the bilinearized contact homology. And so here's an outline of the proof. First, we'll use some, again, of course, like every talk at this conference, we'll use some Morse-Bott techniques. The Morse-Bott techniques allow us to write down some really nice, almost complex structure, and that'll give us holomorphic foliations. And everything is kind of too nice. And so if things are too nice, you know you're probably in trouble. And we'll run into some transversality issues. And in order to deal with the transversality issues, we'll do some obstruction bundle gluing type of analysis. And that kind of tells us how to study the problem, but doesn't give us the answer because we have to perturb away non-transversely cut out things. And for that, we'll use some Korenishi techniques. And as a warning, there's kind of a lot of moving parts here. And I'm going to gloss over a lot of the technical details in order to stay focused on the narrative. So I guess if you're not familiar with some of this stuff, then maybe it's propaganda that it's not so bad. And if you are familiar with this stuff, then I'm sorry that there's not kind of more details. So first we start off with describing the Morse-Bott contact forms. So to start, we take alpha naught to be our tau invariant contact structure on our neighborhood of our hypersurface. So recall we're using R, the real line parameterized by tau, times the hypersurface is our neighborhood. And in this case, each Reeb orbit in the dividing set will give us a real line of Reeb orbits in the neighborhood. And so here in my picture, here's my hypersurface. I have a tau vector pointing out, that's my kind of normal direction. And then I have an arc parameterized by variable sigma, which is transverse the dividing set. And so on sort of when sigma's on one side of sigma, the Reeb vector field points upward when we're in the positive region. And so it's just pointing upwards in the positive region. We cross the dividing set, and then the Reeb vector field is just tangent to the dividing set. We go into the negative region, and the Reeb vector field points downwards. So I'll just call that R naught. And so if you know a little bit about sutured contact homology, you know this is, well, obviously it's no good because it's Morse-Bott and not Morse. But if you know a little bit about sutured contact homology, you know that in order for it to be well defined, your Reed vector field has to look a certain way on the boundary of your contact manifold. And so the way to do that for a convex hypersurface is to make this line of Reed orbits into a single hyperbolic type of normal bundle Reed orbit. And so, so we have our, for each Reed orbit in the dividing set now, we have a single Reed orbit inside of our neighborhood of our convex hypersurface. And if we project the Reed vector field onto the normal bundle of the dividing set, then it looks like the Hamiltonian flow around an index 1 critical point on the disk. And so the Conley-Zender index, when you look at these kind of index 1 flows, it doesn't do anything, it's just 0. And so the Conley-Zender index of our orbit is the same thing as this Conley-Zender index of the orbit in the dividing set, but the contact homology grading bumps up 1 because n goes up by 1. And so our grading of a Reed orbit gamma inside of the neighborhood of our convex hypersurface is the grading inside of gamma plus 1. And so this is a generalization of construction which Vaughan does in the dimension 2 case, and for convex hypersurfaces specifically. And regarding these kind of hyperbolic normal bundles, there's also this paper which came out last year of Cote and Pateau-Chaplot, where they study kind of context submanifolds where they have a codimension 2 with different types of normal bundles. And so our next step is we're going to define our almost complex structures. And also, like quite a few of the talks here, we're going to use holomorphic foliations. And so we choose our J so that when epsilon is equal to 0, which is the degenerate Morse-Bott case, we have that each slice, tau times a positive or negative region, this has a holomorphic lift to the symplectization, which I'll call RS times the neighborhood of the convex hypersurface. Now, when we break the Morse-Bott symmetry with epsilon greater than 0, the slice 0 times tau is equal to 0 times the convex hypersurface. The tau equals 0 times the positive and negative regions still have holomorphic lifts. And for all epsilon, the symplectization of the dividing set is holomorphic inside of the symplectization of our neighborhood of our convex hypersurface. And so we take our picture from before, we have the convex hypersurface multiplied by the real line for our symplectization direction. And if we project these holomorphically lifted, now codimension 2 hypersurfaces to the symplectization direction plus the normal direction to the dividing set, it'll kind of look like this sneaker logo type thing, where the dividing set times the symplectization of the dividing set is holomorphically embedded inside of the symplectization of our neighborhood of our convex hypersurface. And so consequently, when epsilon is equal to 0, we can see all of the holomorphic curves because using this foliation. And so intersection positivity tells us that the holomorphic curve has to either be contained in a leaf of our foliation, which is one of these positive or negative regions holomorphically lifted, or it lives exactly in the symplectization of the dividing set. And when epsilon is greater than 0, we can use some Wendell automatic transversality results on the normal bundle to the manifold to say that if we have a transverse plane, which is inside the positive or negative region, this will give us a transverse plane in the symplectization of our neighborhood of our convex hypersurface. And so these techniques, as I said, they're used in some of the talks already here. So these holomorphic foliations by codimension 2 submanifolds are used to study planar, iterated planar, spinal open books, and bourgeois context structures. Maybe not the most recent version of the bourgeois context structure paper, I'm not sure, but maybe according to what Jonathan was talking about yesterday. But this is originally due to Basile, Bach, and Hofer when they're proving the Weinstein conjecture for planar contact-free manifolds.
When you say transverse plane, you mean a holomorphic plane so that the linearization of D bar is transverse?
Yes, exactly. Sorry, I should have been more verbose. Yeah, so when I say a holomorphic curve is transverse, that means its linearized operator is transversely cut out, or it's surjective.
Just wanted to make sure you didn't mean that the plane itself is transverse to anything.
Yeah, sorry, I should.
That's fine.
Okay, so now, so now we'll get into talking more about some of these transversely cut out things. And so, so everything is great for epsilon equal to 0. We know what all the holomorphic curves look like. They're either stuck in these leaves of this foliation, or they're exactly in the symplectization of the dividing set. So we can just plug in Bourgeois' PhD thesis, and then we're done, right? And so what Bourgeois' PhD thesis says in this case, when there's familiar with it, there's no Morse flow lines to worry about. It says that for epsilon greater than 0, the contact homology differential will count SFT buildings made out of the epsilon equals 0 curves, the Morse-Bott curves, whose total index is equal to 1. But that only works if all of the curves we're starting out with are kind of transversely cut out. And that's not going to be the case for us. So if I take a holomorphic curve, I'll call U check, which is mapped into the symplectization of the dividing set. And because the dividing set is purple, I'll color those holomorphic curves purple. This gives us a holomorphic curve in the symplectization of our neighborhood of our convex hypersurface, just by composing with the inclusion. And we have a problem, which is that this new holomorphic curve is the index of the old holomorphic curve plus the Euler characteristic. And that could be very bad. And so I guess if you like, these kinds of plus Euler characteristic type of things happen every time you do a stabilization. Like if you want to compute a Haggard floor homology, you have kind of similar issues that makes things less computable. But luckily, this is sort of more abstract, but somehow easier to compute with, and which we'll see because we can actually compute. And so here's an example of sort of a problem that can pop up. So in this figure, I have a holomorphic curve in the dividing set with 3 negative punctures. And then I cap off 2 of the negative punctures with planes in the positive and negative regions. And this will give me a configuration whose total index is 1. But that's because the top index, the index of the top piece is -1. And then the indices of the bottom pieces will be +1. So I'll get a total index 1, top piece -1, bottom 2 pieces +1, and that's very bad because now if we're trying to follow what happens in Bourgeois' thesis, we have to carry out some gluing arguments, and now we're going to try to glue things together where one of the pieces is not transversely cut out, and some of the pieces are transversely cut out. And then there's another problem to deal with, which is that even without the gluing, if we just take this purple piece, just the piece that sits in the dividing set, if we want to count index 1 curves, that means just when we look at the curve just in the dividing set, it might have to have index 3. So now we might have to do some kind of obstruction bundle count over a moduli space of index 3 curves. And that's also really bad, maybe worse. So, so what are we going to do? Luckily, we have this Hutchings-Taubes obstruction bundle gluing theory, which can help us figure out how to navigate these issues. And so to apply the obstruction bundle gluing analysis, my kind of understanding of it is that if you can understand the kernels and co-kernels of your linearized operators, then you can actually make some progress on this. And if you can't, then you might be in deep trouble. But we're kind of lucky in this case. So, so what we want to know is we have a holomorphic curve inside of the symplectization of our neighborhood of our convex hypersurface, and it's determined by a holomorphic curve just in the symplectization of the dividing set. And we want to understand the kernels and co-kernels associated with this. And so we're going to use a variation of Bauhanda's L-simple setup on this normal bundle, and that makes our linearized operator really nice. And it splits, our linearized operator splits into the linearized operator just for the dividing set, plus a normal linearized operator. And the normal linearized operator acts on sections of the normal bundle and sends them to 0, 1 forms on the surface. And if you write the equations for this, they actually look really nice, and you think, oh, maybe I can kind of explicitly solve them, and you can. And so, so you do a little bit of calc 2 and calculate some integrals and to analyze these things. And the result is that if the domain of your holomorphic curve is a plane, then the normal linearized operator is surjective of index 1. If your domain of your holomorphic curve is a cylinder, then the index of the normal linearized normal operator, I'm screwing my words, is surjective of index 0. And when the domain has negative Euler characteristic, which we know is the bad case, the normal linearized operator is injective, and its co-kernel can be explicitly trivialized. And so I'll note, if you know kind of how Wendell's automatic transversality works, this first case, when we have the domain as a plane, falls within the automatic transversality range, and then everything else doesn't work out. So we have to do some analysis by hand. And so how do we analyze these things? So we identify the kernel of the normal linearized operator, or sorry, the co-kernel of the normalized linear operator with the kernel of the dual operator. And these kernel elements satisfy some PDEs, so they look really nice. In particular, they have Hoffer-Wierzbowski-Zehnder expansions near their cylindrical ends, just in the same way that holomorphic curves have eigenvalue decompositions. And so we can say, let's look at the coefficients of these eigen expansions and see if we can read off some useful information. And it ends up that when you have such an element, it's completely determined by the coefficients of its asymptotic eigenfunction, which has winding number 0, just at the negative punctures. So in particular, if we have m negative punctures, we can represent an element of the co-kernel bundle by just an m-dimensional vector. And it has to satisfy that the sum of the elements are 0. And so that's the same thing as saying that the co-kernel of the normal linearized operator is equal to Rm divided by the line in Rm, which is just the diagonal, the span of 1, 1, 1, 1, 1, 1. Okay, so now, any questions so far before I proceed forward? Okay, so now this is great, but there's some hope we can solve these gluing problems because we've explicitly trivialized our normal bundles. And note we've done this for parameterized curves, meaning that we've sort of fixed the orderings of the negative punctures. And so the obstruction bundle gluing analysis tells us that when you try to glue a transversely cut out thing to a non-transversely cut out thing, all of the problems are kind of concentrated on the non-transversely cut out thing. And so that's where we have to carry out the analysis. And so for us, when we have these multi-level configurations, we only need to study the analysis sort of all happens at the top level, which is the curve contained in the symplectization of the dividing set. And so again, we're just reducing this to analysis of vectors in Rm. And so what happens is we try to pre-glue these curves, and we have neck stretching parameters for each plane that we're gluing onto a negative end of our curve inside of the dividing set. And when we stretch out really far, it gives us an obstruction vector, which is just a vector in Rm. And we can, up to some kind of terms which don't matter, we can explicitly describe what it is, which is that the coefficients decay exponentially in the size of the neck stretching parameter. And they do so with positive sign when we glue on a negative plane from S minus, and they do so with negative sign when we glue on a plane from S plus. And so we know that we can glue if and only if our obstruction vector lives in this diagonal subspace of Rm, which is clearly never possible. So great, so we shouldn't perturb, right? But if we don't perturb, then we still have the curves in the middle, which are not transversely cut out. So we have no choice but to perturb. And how will we do that? We'll add some perturbation vectors to our obstruction bundle. And again, I have to do this in a kind of way which doesn't depend on the ordering of the punctures. And in order to do that, we use this Fukaya at the SFO cubes multi-section technology. And so if we have, for example, 3 negative punctures, we have our obstruction vector has length 3. And so we take all permutations of the vector row, 2 row, 3 row, for example, where row is a small number. And so in general, if we have m negative punctures, we'll have m factorial perturbation vectors to deal with. And so this is going to give us some weights in the count, the count of curves, which defines the bilinearized contact homology. But that aside, when we want to count what our holomorphic curves are, if we can glue, that's the same thing modulo sort of the implicit function theorem. Is counting solutions to our obstruction vector, which we have an explicit description for, minus our perturbation vector, which we also have an explicit description for, living in this diagonal line in Rm. And so this counts all the curves, and this is and so this count with vectors in Rm is just a friendly arithmetic problem, and so it can be explicitly solved. And this tells us what our counts of holomorphic curves are now. And so the end result is that when we count our index 1 holomorphic, our Morse-Bott buildings with perturbations, if we have one negative end, these perturbation vectors just kill off everything. So there's no holomorphic curves to count with more than one negative end after gluing. When we have exactly one negative end after gluing, we get exactly the bilinearized contact homology differential. That just comes from the arithmetic of this vector problem. And we have no negative ends. The only things to count are just planes inside of the positive and negative regions. And so when we count those with signs, we get the augmentation on the positive side minus the augmentation on the negative side. And that completes the proof. So now we know exactly what the differential in our contact homology looks like. And then to go from this to the algebraic Schur criterion is just some not so difficult homological algebra. And so I guess the high-level takeaways are, if you kind of know asymptotics, you know everything about these kind of obstruction issues, and you can usually write things down pretty explicitly. And then, so I guess this is more propaganda for if you don't know this stuff, or maybe thinking about learning it, maybe it sounds weird. I used to think it was quite scary. So the asymptotics parameterize everything in a very nice way, if you're lucky. The obstruction bundle gluing is also very friendly, assuming that your obstruction bundles are nice. And Kuranishi makes all of your gluing computations actually much easier. And that's the end of the talk.
Is there any question? But Jerry, you want to
do you have any ideas of how you could use gluing results to computations of contact homology for closed manifold using decomposition by convex hypersurfaces?
I mean, yeah, of course I want to think about that. I mean, I have some ideas, but nothing, I mean, I think, there's a really interesting problem would be, so, fill in the blanks. You have open book decomposition, Fukaya category of the page, that should, SFT, there should be some kind of connection there. I don't know what it is, but maybe my hope is that maybe something like this will help fill in with the details there. But that's kind of very speculative.
Okay, I have a question. So it's I got lost when the Kuranishi stuff came in, because in my mind the obstruction bundle technique is exactly when you can do things without going to this fancier technology. So why do you need both?
So why do you need both? So So I guess so ultimately the obstruction bundle gluing says you can reduce it to kind of an affine linear algebra problem. You're trying to solve, find a linear map which sends this vector to that vector. And you can kind of parameterize all your co-kernel bundles. And so without perturbations, you just kind of solve that problem, and all of the vectors involved just come from the geometry of the ambient manifold. And so the issue is that in our case, we know that we have to perturb, because if we don't perturb, we have these non-transversely cut out curves, which are the ones inside of the dividing set. And so there's I guess there's two options. One would be you could try to geometrically perturb, which is just change the almost complex structure J on the manifold. And maybe the problem is probably solvable, or I mean, it's probably approachable from that perspective. But I think I think when you're doing these kind of closed string theories, you always have to worry about multiple covers. So I guess a priori, there's no way to avoid Kurenishi or some kind of perturbation theory. You know, there's also kind of this the John Pardon style, and obviously polyfolds. So I may be far less qualified to comment on those kinds of techniques, but maybe I think maybe the Kurenishi or some kind of perturbation theory is just absolutely unavoidable.
I have a question. So, so first of all, about algebraically overtwisted, I think this was much earlier. It's probably yes, or I don't know. I mean, it was just that we had several candidate notions that were all equivalent. And anyway, no. But my real question was, since I have a lot of problem with algebra and all these things, so if you had this situation with this convex hypersurface, and you were taking, let's say, a symplectic, so this is all in a contact manifold, and you had the symplectic filling, let's say.
Mm-hmm. Of the ambient contact manifold.
On the ambient, could you somehow, because I don't really understand with, well, I have problems with this algebraic setup, but could you think that somehow the holomorphic curves on one side and on the other side somehow can be pushed into the symplectic filling to give, I don't understand why having the epsilon plus and epsilon minus different values would lead to, let's say, to contradiction to fillability. Would it somehow be that you have a one-dimensional modular space, and on one side it would look differently than on the other side, or something like, so you somehow can connect from one half of the convex hypersurface, the modular space, to the other through the filling, or something like this? Or what is the geometric idea of why?
Yeah, maybe that's a great question. I don't know. Maybe I guess so I guess what could happen is if you have some holomorphic planes, right, and they just live in the symplectization end, right, and then you push them down into the filling. Either you get maybe some, or if you have bubbling, then you know that you know that there's a contradiction in that the filling can't exist. So maybe it's like the holomorphic curve has to like start out in S minus and then sweep over to go to S plus. I'm not quite sure. Yeah, that would be kind of my guess as to maybe what should happen, but I don't know. That's an interesting question.
So sorry, but isn't the algebraic answer somehow that if you have an augmentation, if you have a filling, it doesn't mean that you have no constant terms, but the constant terms become sort of a killable.
Yeah, here for the.
Something like that, isn't that what you said?
Yeah, for here. So this is. I mean, you would help me out with this. So the story is that if this is zero in homology, then you can show that it's zero, like it's chain homotopic to zero on the chain level. And then when you have that chain, if you can show that there's a chain homotopy to zero, then you can show that the contact homology algebra has an explicit augmentation.
And the point is somehow that this DGA that you have there is a bit unusual because it only has linear and constant terms. So
Yeah.
augmentability equation becomes just something quite stupid, I think.
Yeah, I think there's probably. So I think this kind of thing can probably be improved a lot. So I know that in the Legendrian case, I mean, you know this stuff like way better than I do, but I know that there exists examples, right, of Legendrian DGAs which are non-zero but don't have any augmentations. And so I guess the same thing presumably could happen in contact homology, but it seems like that's not the case here. It would seem that it's kind of like,
this is a very particular type of DGA. It's not any kind of DGA. You only have the DCH is the full DGA differential. And in this case, you have a constant plus some kind of linear terms.
yeah.
If you, I don't know, take a piece of paper and write down the fact when, or the kind of equation when this actually admits an augmentation, well, then you get some equations that are much simpler. Probably that can explain Klaus's question, I guess.
Yeah, so in this case, so you can add another equivalent condition on here, which would be that that there exists an augmentation. But that's kind of
it's induced by a filling. Then, if there would be a filling of this hypersurface, it would be induced in such a relation.
Yeah, well, yeah. I guess the filling here is just like kind of an the augmentation is just like algebraic augmentation, but yeah, I kind of don't know what's going on in terms of geometric fillability, but maybe that imposes some kind of special conditions.
Hi, I have a question. In the perturbation, you use the Cornish perturbation. So the number of gluing will depend on the perturbation you choose, right?
Oh yes, so you get some rational counts, and so